Welcome to a deep dive into one of the most transformative advancements in artificial intelligence, self-supervised learning, or SSL. For years, the progress of AI, particularly in areas like computer vision and natural language processing, was heavily reliant on vast amounts of meticulously labeled data. This manual annotation process is often called the data labeling bottleneck. It's incredibly expensive, time-consuming, and labor-intensive, often requiring expert human annotators. Self-supervised learning presents a revolutionary paradigm shift by finding ways for models to learn powerful, generalizable representations directly from raw, unlabeled data. It's about letting the data teach itself, uncovering intrinsic structures and patterns without explicit human guidance. This ability to extract meaningful insights from the sheer volume of information available to us today is what makes SSL such a compelling and critical area of AI research and application, promising to unlock new levels of intelligence. To truly appreciate self-supervised learning, it's crucial to understand its contrast with traditional supervised learning. In supervised learning, a model learns by being presented with input data paired with the correct output label. Think of showing a model thousands of pictures of cats, each explicitly labeled cat. This requires immense human effort, with annotators spending countless hours categorizing and labeling data. This process is not only high cost, but also incredibly time-consuming, becoming a major constraint as datasets grow. Self-supervised learning, however, cleverly generates its own supervisory signals from the data itself. It's like giving a puzzle to a model without providing the final picture, but rather hints from the pieces themselves, allowing it to learn the underlying structure. This automatic supervision from raw data represents a fundamental shift in how AI models acquire knowledge, moving away from explicit human labeling towards more autonomous and scalable learning. At the heart of self-supervised learning are pretext tasks. These are cleverly designed auxiliary tasks that a model can solve using only the information present in the unlabeled input data itself, without needing any external human labels. The key insight is that in order to solve these pretext tasks, the model must first learn a deep understanding of the data's underlying structure and features. For instance, in natural language processing, a common pretext task is masked language modeling, where certain words are hidden in a sentence, and the model must predict them based on context. In computer vision, a model might be tasked with predicting the rotation applied to an image, or solving a jigsaw puzzle by reassembling shuffled image patches. By solving these tasks, the model isn't just learning to predict a specific output, it's learning rich, meaningful representations of the data that captures semantic and syntactic information, which can then be transferred to solve more complex downstream tasks effectively. Among the various methodologies within self-supervised learning, contrastive learning has emerged as a particularly powerful paradigm. The core idea behind contrastive learning is to learn representations by ensuring that similar data points are pulled closer together in an embedding space, while dissimilar data points are pushed further apart. This is often achieved by creating positive pairs, different augmented views of the same data sample, and negative pairs, different data samples altogether. Architectures like Siamese networks are commonly used, where two identical networks process these pairs. The model is then trained with a contrastive loss function to maximize agreement between positive pairs and disagreement between negative pairs. Landmark models like SimCLR, Simple Framework for Contrastive Learning of Visual Representations, and MoCo, Momentum Contrast, have significantly advanced the state of the art in this area, demonstrating how effective contrastive learning can be in generating highly useful and robust representations for various downstream tasks, particularly in computer vision. Self-supervised learning has had a monumental impact on natural language processing, fundamentally changing how we develop and utilize language models. The breakthrough came with models like BERT, bidirectional encoder representations from transformers, and the GPT series, generative pre-trained transformer. These models are pre-trained on colossal amounts of raw, unlabeled text data from the internet. Think billions of words. BERT, for example, uses masked language modeling as its primary pretext task, predicting masked words within a sentence. GPT models, on the other hand, leverage next token prediction, learning to anticipate the subsequent word in a sequence. By performing these tasks on vast corpora, these models learn exceptionally rich contextual representations of language, capturing grammar, semantics, and even some world knowledge. This pre-training phase allows them to be fine-tuned with relatively small labeled datasets for specific downstream tasks, like sentiment analysis, machine translation, or question answering, achieving unprecedented performance and efficiency. The advancements in self-supervised learning are equally transformative in the field of computer vision. Traditionally, training robust image recognition models required datasets like ImageNet, with millions of images painstakingly labeled by humans. SSL allows computer vision models to learn powerful visual features directly from raw image data, circumventing this labor-intensive process. Pretext tasks in computer vision often involve image manipulations. For instance, a model might be asked to predict how an image was rotated, image rotation prediction, or to reconstruct an image from shuffled jigsaw puzzle patches. More advanced methods, building on contrastive learning, create different views of the same image, e.g., by cropping, color jittering, or blurring, and train the model to recognize them as belonging to the same underlying image. By learning to solve these visually challenging puzzles, models develop a sophisticated understanding of features like edges, textures, shapes, and object parts, without ever being told what a cat or a car explicitly is. These learned features are then highly effective for downstream tasks like object detection, image segmentation, and facial recognition, often matching or even surpassing supervised benchmarks. One of the most profound advantages of self-supervised learning is its inherent data efficiency, particularly regarding labeled data. In an era where data is abundant but human labeling resources are scarce, SSL offers a critical pathway to scale AI. It dramatically reduces the reliance on expensive and time-consuming human annotation efforts, which can cost millions of dollars and thousands of hours for large-scale projects. By automatically generating supervisory signals, models can leverage the virtually infinite supply of unlabeled data available on the internet, billions of images, text documents, and videos. This capability not only slashes development costs and accelerates deployment timelines, but also democratizes AI by making powerful models accessible even when labeled datasets are small or non-existent for niche domains. The data efficiency of SSL means we can train more sophisticated, generalized AI models faster and at a much lower financial and labor cost, leading to an estimated 100x less labeled data needed compared to purely supervised approaches. While self-supervised learning offers immense potential, it's not without its challenges. One primary hurdle lies in designing effective pre-task tasks. A poorly designed pre-task task might lead the model to learn trivial or irrelevant features, failing to capture the rich, transferable representations desired. Crafting tasks that force the model to genuinely understand the underlying data structure requires significant research and empirical tuning. Secondly, the computational resource demands for pre-training large self-supervised models can be enormous. Training models like BERT or GPT-3 involves hundreds or thousands of GPU hours and substantial energy consumption, making them expensive to develop and run. Lastly, there's the ongoing challenge of mitigating biases in learned representations. If the vast unlabeled datasets used for pre-training contain biases, e.g., societal stereotypes, underrepresentation of certain groups, the self-supervised model will inevitably learn and potentially amplify these biases, leading to unfair or discriminatory outcomes in downstream applications. Addressing these challenges is crucial for the responsible and widespread adoption of SSL. Looking ahead, the future of self-supervised learning is incredibly exciting and holds the promise of even more profound breakthroughs. One major direction is multimodal learning, where models learn from diverse data types simultaneously. combining text, images, audio, and even video. Imagine a single model that understands a scene not just from its visual elements, but also from the accompanying sounds and descriptive text, creating a more holistic and human-like comprehension. Another significant trend is the push towards general AI systems. SSL is a key component in building foundation models that can perform a wide array of tasks without being specifically trained for each, moving us closer to truly intelligent and adaptable AI. Furthermore, integrating SSL with reinforcement learning could lead to agents that learn powerful internal world models from raw sensory input, enabling them to explore and interact with environments more intelligently. As research progresses, we anticipate SSL will continue to expand its influence, leading to more robust, efficient, and versatile AI systems that can learn effectively from the world's vast, unstructured data. In conclusion, self-supervised learning represents a monumental leap forward in the field of artificial intelligence. It adeptly addresses the data labeling bottleneck that has historically hindered the scalability and cost-effectiveness of AI development. By enabling models to learn powerful, generalizable representations directly from the vast oceans of unlabeled data, SSL is driving innovation across virtually every domain of AI, from natural language understanding to computer vision and beyond. It empowers us to build more efficient, robust, and versatile AI systems that can adapt to new tasks with minimal additional supervision. This foundational shift in how machines learn is not just an incremental improvement, it's a paradigm change that democratizes access to advanced AI capabilities and accelerates the pace of discovery. As we continue to refine pretext tasks and develop more sophisticated architectures, the transformative power of self-supervised learning will undoubtedly continue to unlock unprecedented potential, shaping the future of intelligent systems for decades to come.